Welcome to the JEE Prep Community Chemistry Masterclass. In this complete lecture, we will study classification of elements and periodicity in properties. Our goal is not to memorize a collection of arrows. Our goal is to understand why those arrows exist. The central idea of the entire chapter is this chain. Electronic configuration leads to nuclear charge. Nuclear charge and shielding determine effective nuclear charge. Effective nuclear charge determines size and electron attraction, and those quantities determine ionization enthalpy, electron gain enthalpy, electron negativity, metallic character, and chemical behavior. If you can follow this chain, you can derive the answer to an unfamiliar JEE question instead of depending on a memorized rule. Let us begin with a simple thought experiment. Imagine that you have 63 strangers in a room and you need to organize them so that people with similar behavior stand together. You would look for a pattern. Chemistry faced the same problem. In 1800, only 31 elements were known. By 1865, the number had grown to 63, and each element appeared to have its own set of properties. Studying every element and every compound independently was becoming impossible. Classification was necessary because it could group similar elements, reveal recurring patterns, and possibly predict properties that had not yet been observed. The first important attempt was Dobereiner's law of triads in 1829. He found groups of 3 elements in which the atomic mass of the middle element was approximately the average of the other two, and the chemical behavior was intermediate. Consider lithium, sodium, and potassium. Their approximate atomic masses are 7, 23, and 39. The average of 7 and 39 is 23, exactly the mass of sodium. Calcium, strontium, and barium form another triad, as do chlorine, bromine, and iodine. But the limitation was serious. Only a few groups fitted the rule. The triad was not wrong, it was simply an incomplete glimpse of periodicity. In 1865, Newlands proposed the law of octaves. When elements were arranged by increasing atomic mass, every 8th element resembled the first, like the 8th note repeating the first note in music. The pattern worked reasonably well only up to calcium. For heavier elements, it broke down, and the scheme had no room for undiscovered elements or for the noble gases that were discovered later. Then came Mendeleev in 1869. He arranged elements mainly by increasing atomic mass, but he prioritized chemical similarity when the two principles conflicted. His periodic law said that the properties of the elements are periodic functions of their atomic weights. His boldest decision was to leave gaps in the table. He predicted an unknown element below aluminium, calling it eka aluminium, and another below silicon, calling it eka silicon. His predictions were remarkably accurate. For eka aluminium, he predicted an atomic mass of 68 and a density of 5.9 grams per cubic centimeter. Gallium was later discovered with an atomic mass close to 70 and a density of 5.94. For eka silicon, he predicted an atomic mass of 72. Germanium was later found with an atomic mass of 72.6. These successes showed that a good classification system could predict nature, not merely arrange known facts. Mendeleev's table still had anomalies. Strict atomic mass order would place argon after potassium, cobalt after nickel, and tellurium after iodine, but the chemical similarities required the opposite. The final breakthrough came from Moseley in 1913. His X-ray experiments showed that the fundamental ordering quantity was atomic number, not atomic mass. Atomic number is nuclear charge, the number of protons, and in a neutral atom, it is also the number of electrons. That leads to the modern periodic law. The physical and chemical properties of the elements are periodic functions of their atomic numbers. Argon has atomic number 18 and potassium has atomic number 19, so argon correctly comes first. Cobalt has atomic number 27 and nickel 28. Tellurium has atomic number 52 and iodine 53. The anomalies disappear. Stop and think for a moment. Why were Mendeleev's gaps a strength rather than a weakness? The answer is that the gaps allowed him to make testable predictions. A scientific model is powerful when it can predict missing information. In the rest of this lecture, we will see that the modern table is even more powerful because its repeating pattern is generated by electronic configuration and nuclear charge.
Now let us build the modern periodic table from electronic configuration. The long-form table has 7 horizontal periods and 18 vertical groups. The period number is the highest principal quantum number present in the ground state electronic configuration. It tells us the outermost occupied shell. It does not mean that every electron is in that shell. The first period fills the 1s subshell
and contains 2 elements. The second and third periods fill S and P subshells and contain 8 elements each. The fourth and fifth periods include S, D, and P filling and contain 18 elements each. The sixth and seventh periods can contain 32 elements because the F subshell is also involved. Elements in the same group have similar valence shell configurations, so they often have similar chemistry. Group 1 has the general outer configuration NS1 and is called the alkali metal group. Group 2 has NS2 and is the alkaline earth group. Group 13 has NS2 NP1. Group 14 has NS2 NP2. Group 15 has NS2 NP3. Group 16 has NS2 NP4. Group 17 has NS2 NP5 and is the halogen group. And group 18 has a completed valence shell NS2 NP6 except helium, which is 1s2. The table is divided into 4 blocks according to the subshell that receives the differentiating electron. The S block contains groups 1 and 2 and has NS1 or NS2 configurations. These elements are mostly reactive metals. The P block contains groups 13 through 18 and includes metals, metalloids, non-metals, and noble gases. The D block contains groups 3 through 12 and has a differentiating electron in the N-1d subshell. It is the transition region with variable oxidation states and often colored ions. The F block contains the lanthanoids and actinoids. They are placed in the bottom 2 rows to keep the table compact, but lanthanoids belong to period 6 and actinoids belong to period 7. There are 2 special placement ideas to remember. Helium has the configuration 1s2, so by subshell filling, it looks like an S block element. But its shell is completely filled and its chemistry is that of a noble gas, so it is placed in group 18. Hydrogen has 1s1, like an alkali metal, but it can also gain an electron and resemble a halogen. That is why hydrogen is treated as a special element at the top of the table. Now, let us create a JEE algorithm. First, write the ground state electronic configuration. Second, identify the highest N, that gives the period. Third, identify the subshell receiving the last differentiating electron, that gives the block. Finally, determine the group. For the S block, group number is the number of valence S electrons. For the P block, group number is 10 plus the total number of valence electrons. For the D block, group number is usually the sum of N-1d electrons and Ns electrons. Worked example 1. Atomic number 35. This is bromine. Its configuration is argon core followed by 3d10, 4s2, 4p5. The highest N is 4, so bromine is in period 4. The differentiating electron enters P, so it is P block. The outer shell has 7 electrons, so it belongs to group 17. Worked example 2. Atomic number 26. Iron has argon core 3d6, 4s2. The highest N is 4, so period 4. The differentiating subshell is D, so it is D block. For a D block element, 6 plus 2 gives group 8. Stop and think. An element has the configuration argon core 3d10, 4s2, 4p3. The highest N is 4. The last electron enters P. There are 5 valence electrons. Therefore, the element is in period 4, group 15, P block, and it is arsenic. Do not rely on the visual position alone. Make the configuration do the work. This structure matters because periodic properties repeat whenever similar valence configurations repeat. The next question is, what physical quantity controls the strength of attraction between the nucleus and an outer electron? That quantity is effective nuclear charge.
We now reach the master key of the chapter, effective nuclear charge, written as Z effective. An outer electron does not experience the full positive charge of the nucleus because inner electrons screen or shield it. The conceptual relation is Z effective equals Z minus sigma, where Z is the actual nuclear charge and sigma is the shielding constant. Imagine a nucleus pulling an outer electron with a rope. The nucleus provides the pull, but inner electrons stand between them and partially block that pull. The outer electron therefore experiences a smaller net attraction than the total nuclear charge. This net attraction is effective nuclear charge. Shielding is not identical for every orbital. Inner shell electrons shield strongly. Electrons in the same shell shield one another only weakly. Across a period, electrons are added to the same principal shell, so the core remains almost unchanged and same shell shielding does not completely cancel the extra proton. Down a group, a new shell is added. The new inner shell provides significant shielding and the outer electron is also farther from the nucleus.
Now, penetration. Penetration is the ability of an electron in an orbital to approach the nucleus. For orbitals with the same principal quantum number, the order is S greater than P greater than D greater than F. An S electron spends more of its probability close to the nucleus, feels greater effective nuclear charge, and lies lower in energy than a P electron of the same shell. This point will later explain why beryllium has a higher first ionization enthalpy than boron. Let us derive the across period trend. Consider lithium through neon. The nuclear charge increases one proton at a time. The newly added electrons enter the same second shell, while the 1s2 core remains unchanged. Since same shell shielding is weak, the increase in nuclear charge wins. Z effective increases from left to right. When Z effective increases, the outer electron cloud is pulled closer. Atomic radius decreases. The electron becomes harder to remove, so ionization enthalpy increases. A bonded atom attracts shared electrons more strongly, so electronegativity increases. The atom becomes less metallic and more non-metallic. In other words, across a period, Z effective rises, radius falls, ionization enthalpy rises, electronegativity rises, and metallic character falls. Now, derive the down group trend. Compare lithium, sodium, and potassium. Each step adds a new principal shell. The outer electron is farther from the nucleus and is shielded by additional inner shells. The nuclear charge does increase, but the distance and shielding effects dominate. Therefore, radius increases, ionization enthalpy decreases, electronegativity decreases, and metallic character increases. For alkali metals, losing the outer electron becomes easier, so reducing tendency and reactivity increase down the group. This is why the arrows in the periodic table are not independent facts. They are different consequences of the same physical picture. Stop and think. Which outer electron experiences higher effective nuclear charge? The 3s electron of sodium or the 3s electron of magnesium? Both have the same neon core. Magnesium has one additional proton, while same shell shielding is nearly the same. Therefore, magnesium has higher Z effective, a smaller radius, and a higher first ionization enthalpy than sodium. At the GE advanced level, Slater's rules can be used to estimate sigma numerically. But most trend questions do not need a precise number. They need relative reasoning. Compare Z, compare shielding, compare shell number, and then decide which electron is held more strongly. Keep the causal chain in mind. Electronic configuration determines the shell and subshell. Nuclear charge and shielding determines Z effective. Z effective determines how tightly the electron cloud is held, and that determines the periodic properties. We will now apply this mechanism to atomic and ionic radius.
Let us now study atomic and ionic radius. An atom does not have a sharp outer boundary because the electron cloud fades gradually. Therefore, radius is defined operationally from internuclear distances. A covalent radius is half the distance between identical atoms joined by a covalent bond. A metallic radius is half the distance between adjacent nuclei in a metal crystal. A van der Waals radius is used for non-bonded atoms, especially noble gases. This difference in definitions creates an important JEE trap. Do not directly compare a noble gas van der Waals radius with the covalent radius of a neighboring halogen and then claim the periodic trend has failed. The measurement conventions are different. Across a period, atomic radius decreases. The principal shell remains the same, but nuclear charge increases and same shell shielding is relatively weak. Effective nuclear charge therefore rises and pulls the cloud inward. In period 2, the verified NCRT covalent radius values go approximately from lithium at 152 picometers to fluorine at 64 picometers. In period 3, sodium is about 186 picometers, while chlorine is about 99 picometers. Down a group, radius increases. A new principal shell is added, and that distance effect is much larger than the modest increase in effective nuclear charge. In group 1, the radius grows from lithium through sodium and potassium to rubidium and cesium. Now compare ions with their parent atoms. A cation is smaller than its parent atom. Why? It has lost electrons but retains the same nuclear charge. Electron-electron repulsion decreases and the remaining electrons are held more tightly. For example, sodium has an atomic radius of about 186 picometers, while sodium plus is about 95 picometers. An anion is larger than its parent atom. It has gained an electron without gaining a proton. Electron-electron repulsion increases and the average attraction per electron decreases.
Fluorine is about 64 picometers as an atom, while fluoride is about 136 picometers. The most powerful radius technique is the isoelectronic series. Isoelectronic species have the same number of electrons. If the electron count is fixed, compare nuclear charge. More protons pull the same electron cloud more strongly, so higher Z means smaller radius. Consider the 10 electron series. Nitride N3- has Z7. Oxide O2- has Z8. Fluoride F- has Z9. Sodium plus has Z11. Magnesium 2+ has Z12. Aluminium 3+ has Z13. All have 10 electrons. Therefore, the decreasing radius order is N3- greater than O2- greater than F- greater than Na+, greater than Mg2+, greater than Al3+. In increasing order, reverse that list. The sentence to remember is not an arrow. It is same electrons, increasing nuclear charge, decreasing radius. Now solve the authentic JEE main question from 7 April 2025 evening shift 2. Choose the incorrect trend in atomic radii. Option A says radius of bromine is less than radius of potassium. Option B says radius of magnesium is less than radius of aluminium. Option C says rubidium is less than cesium. Option D says aluminium is less than cesium. Pause and test the relationships. Bromine and potassium are in the same period, but potassium is much farther left, so potassium is larger. A is correct. Magnesium and aluminium are in the same period. Moving left to right, effective nuclear charge increases and radius decreases, so magnesium is larger than aluminium. Therefore, the statement R of Mg less than R of Al is incorrect. The answer is B. Rubidium is smaller than cesium down group 1 and aluminium is smaller than cesium because cesium has an additional shell. Whenever you see a radius question, first classify the comparison, same period, same group or isoelectronic. Then apply one mechanism. Across a period, compare effective nuclear charge. Down a group, compare shell number and shielding. For isoelectronic species, count electrons and then compare nuclear charge. This method is more reliable than memorizing a long list of radii. Next, we will ask a different question. How much energy is needed to remove one of these electrons? That is ionization enthalpy.
Ionization enthalpy is the enthalpy required to remove the most loosely bound electron from an isolated gaseous atom in its ground state. The first ionization process is X gas gives X plus gas plus an electron. It is always endothermic, so first ionization enthalpy is positive and is measured in kilojoules per mole. Successive ionization enthalpies are always increasing. The second electron is removed from a more positive ion than the first, so it is held more strongly. The third is harder still. This gives IE1 less than IE2 less than IE3 and so on. A large jump in successive values is highly informative. Suppose the values are 800, 2427, 3658, 25024 and 32824 kilojoules per mole. The huge jump occurs between the third and fourth ionizations. That means the atom has 3 valence electrons. The first 3 electrons were removed from the outer shell. The fourth would be removed from a stable inner shell. Therefore, the element belongs to group 13. Across a period, first ionization enthalpy generally increases because effective nuclear charge rises and radius falls. Down a group, it generally decreases because the outer electron occupies a higher shell, is farther from the nucleus, and is more shielded. Noble gases lie at the high end because their shells are filled. Alkali metals lie at the low end because one outer NS electron is relatively easy to remove. But JEE questions focus on exceptions. The first exception is beryllium compared with boron. Beryllium has the configuration 1s2, 2s2. Boron has 1s2, 2s2, 2p1. A simple periodic rule might predict boron should have a higher ionization enthalpy because boron has one more proton. But ask which electron is actually removed. Beryllium loses a 2s electron. Boron loses a 2p electron. For the same principal shell, s orbitals penetrate closer to the nucleus than p orbitals. The 2s electron is lower in energy and held more tightly. The 2p electron in boron is higher in energy and is shielded by the 2s pair. Therefore, it is easier to remove.
Experimentally, the first ionization enthalpy of Be is about 889 kilojoules per mole, while B is about 800. Hence, IE of Be is greater than IE of B. The exam sentence is beryllium has a filled 2s subshell, while boron loses a less penetrating higher energy 2p electron. The second exception is nitrogen compared with oxygen. Nitrogen has 1s2, 2s2, 2p3. Hund's rule places one electron in each of the 3p orbitals, giving a half-filled p subshell. Oxygen has 2p4. One of the p orbitals contains a pair. The half-filled p3 arrangement has extra stability associated with symmetry and exchange energy. In oxygen, the paired electrons repel each other. Removing one electron from that paired orbital relieves repulsion, so oxygen loses an electron more easily than nitrogen, despite oxygen having a higher nuclear charge. The measured values are approximately 1402 for nitrogen and 1314 for oxygen. Therefore, IE of N is greater than IE of O. This gives the useful period 2 order. Lithium less than boron, less than beryllium, less than carbon, less than oxygen, less than nitrogen, less than fluorine, less than neon. Notice both reversals. Boron comes below beryllium and oxygen comes below nitrogen. The same orbital logic appears in period 3. Magnesium is greater than aluminium because magnesium loses a 3s electron while aluminium loses a 3p electron. Phosphorus is greater than sulfur because phosphorus is 3p3 half filled while sulfur is 3p4 with pairing. Now attempt the authentic IIT JEE 2009 question. Which order is correct for the first ionization energies? A says B less than beryllium less than nitrogen less than oxygen. B says beryllium less than B less than nitrogen less than oxygen. C says B less than beryllium less than oxygen less than nitrogen. D says B less than oxygen less than beryllium less than nitrogen. Pause and reason. We know B is less than beryllium and O is less than N. Therefore, the correct answer is C. B less than beryllium less than oxygen less than nitrogen. The important lesson is not the option letter, it is the method. Identify the subshell from which the electron is removed, then inspect half filling and pairing before applying the general trend. Stop and think. If first ionization enthalpies of sodium, magnesium, and silicon are 496, 737, and 786, would aluminium be closer to 575 or 760? Aluminium is closer to 575 because it loses a 3p electron, so its IE is lower than magnesium's 3s removal. Ionization enthalpy is therefore a story about attraction, orbital energy, penetration, and electron-electron repulsion. Next, we will see how the same ideas affect an atom that gains an electron.
Electron gain enthalpy is the enthalpy change when an electron is added to an isolated gaseous atom. The reaction is X gas plus an electron gives X minus gas. If energy is released, the electron gain enthalpy is negative. If energy must be supplied, it is positive. Across a period, electron gain enthalpy generally becomes more negative because effective nuclear charge increases and the incoming electron is attracted more strongly. Down a group, it generally becomes less negative because the incoming electron enters a larger shell farther from the nucleus. Halogens tend to have strongly negative values because gaining one electron completes the ns2-np6 configuration. Noble gases have positive values because an extra electron would have to enter a new principal shell. Nitrogen is also unusual because its half-filled 2p3 configuration is especially stable, so adding an electron disrupts that arrangement. Now the famous exception. Chlorine has a more negative electron gain enthalpy than fluorine. The values are approximately minus 328 kilojoules per mole for fluorine and minus 349 for chlorine. At first, this seems surprising. Fluorine is above chlorine, has a smaller radius, and is more electronegative. Why does it not release more energy when it gains an electron? The answer is electron-electron repulsion in a compact shell. Fluorine's incoming electron must enter the small, crowded 2p subshell, which already contains 7 valence electrons. The electron density is high and the repulsion is strong. This repulsion reduces the net energy released. In chlorine, the incoming electron enters the larger 3p subshell. The space is roomier and the repulsion is lower, so more energy is released. Therefore, the electron gain enthalpy of chlorine is more negative than that of fluorine.
The same type of exception explains oxygen and sulfur. Oxygen has a compact 2p shell and a value around minus 141 kilojoules per mole, while sulfur is around minus 200. Again, the larger shell reduces repulsion for the incoming electron. Now clarify three terms that JEE problems often mix. Electron gain enthalpy is a thermodynamic quantity for a gaseous atom and is expressed in kilojoules per mole. Electron affinity is often defined using the opposite sign convention for the energy released. So, a larger positive electron affinity commonly corresponds to a more negative electron gain enthalpy. Electronegativity is different from both. It is a dimensionless bond property describing how strongly an atom attracts shared electrons. Stop and think. Why can fluorine be the most electronegative element and yet chlorine have the more negative electron gain enthalpy? Because the two properties describe different processes. Electronegativity concerns shared electrons in a chemical bond, and fluorine's small size gives it a powerful bond attraction. Electron gain enthalpy concerns a free electron entering a gaseous atom, where fluorine's compact shell creates strong repulsion. Chlorine wins in that gas phase process. A reliable answer writing phrase is fluorine's compact 2p subshell causes greater electron-electron repulsion for the incoming electron, whereas chlorine's larger 3p subshell accommodates the electron with lower repulsion. Before moving on, remember that more negative matters. A value of minus 349 represents more energy released than minus 328. Do not treat the number with the larger absolute value as if the sign did not exist. Read the question wording precisely. The next property is related to electron attraction but is defined inside a bond. That property is electronegativity.
Electronegativity is the ability of an atom in a chemical compound to attract the shared electron pair towards itself. This definition contains the key distinction. Electronegativity is a property of a bonded atom, not the thermodynamic energy change of an isolated gaseous atom. It is dimensionless and is commonly expressed on the Pauling scale, where fluorine is assigned 4.0. Across a period, electronegativity increases. Effective nuclear charge rises and atomic radius decreases, so a bonded atom attracts shared electrons more strongly. Down a group, electronegativity decreases because the bonding electrons are farther from the nucleus and more shielded. On the periodic table, electronegativity increases generally towards the upper right. Fluorine has the highest value among the elements commonly used in JE chemistry. Metals on the lower left have lower electronegativity. Keep the distinction sharp. Fluorine is more electronegative than chlorine, but chlorine has more negative electron gain enthalpy. Fluorine has the strongest attraction for shared electrons in a bond. Chlorine releases more energy when a free electron enters its larger 3p shell. The physical situations are different. Electronegativity also helps assign oxidation states. When a bond is treated as if both shared electrons belong to the more electronegative atom, that atom receives the negative oxidation state. In sodium oxide, oxygen is more electronegative than sodium, so oxygen is assigned -2 and each sodium +1. In oxygen difluoride, fluorine is more electronegative than oxygen. Each fluorine is -1, so oxygen must be +2. This is a common conceptual check. Oxygen is not always assigned -2 when fluorine is present. Now connect the atomic properties to metallic character. Metallic character is the tendency to lose electrons and form cations. A metal generally has a large radius, lower ionization enthalpy, and lower electronegativity. A non-metal generally has a smaller radius, higher ionization enthalpy, and greater ability to attract or gain electrons. Across a period, metallic character decreases because effective nuclear charge increases and electrons are held more tightly. Down a group, metallic character increases because the outer electron is in a higher, more shielded shell and is easier to remove. Electropositive character is essentially the same direction as metallic character. It is the tendency to lose electrons. This gives us reducing and oxidizing tendency. A reducing agent donates electrons, so metals on the lower left are commonly strong reducing agents. An oxidizing agent accepts electrons, so non-metals towards the upper right are commonly strong oxidizing agents. In group 1, reducing tendency increases down the group because ionization enthalpy falls. In group 17, oxidizing tendency generally decreases down the group because the ability to attract an incoming electron becomes weaker with increasing size.
Reactivity is high at both edges of a period, but for opposite reasons. Alkali metals are reactive because they can lose one electron easily. Halogens are reactive because they can gain one electron to complete the noble gas configuration. The center of a period is generally less reactive because neither loss nor gain is as easy. Oxides provide a chemical expression of metallicity. Sodium oxide is basic and reacts with water to form sodium hydroxide. Aluminium oxide is amphoteric. It can react with both acids and bases. Chlorine heptoxide is acidic and reacts with water to produce perchloric acid. Across a period, oxide character shifts from basic through amphoteric towards acidic as the elements become less metallic and more non-metallic. Stop and think. Arrange phosphorus, silicon, beryllium, magnesium, and sodium in increasing metallic character. Begin with the periodic table positions, not memory. Metallic character decreases left to right and increases downward. The correct order is phosphorus less than silicon, less than beryllium, less than magnesium, less than sodium. The unifying message is now visible. High effective nuclear charge gives a smaller atom, higher ionization enthalpy, higher electronegativity, lower metallic character, and greater oxidizing tendency. Low effective nuclear charge or strong shielding gives the reverse. We will consolidate this map before solving the final question set.
We are now ready for the master map. Every periodic trend follows from effective nuclear charge, shell number, shielding, and electron-electron repulsion. Across a period, atomic radius decreases and down a group it increases. For ions, a cation is smaller than its parent atom and an anion is larger. In an isoelectronic series, higher nuclear charge means smaller radius. First ionization enthalpy increases across a period and decreases down a group, with the critical exceptions Be greater than B and N greater than O. Electron gain enthalpy becomes more negative across and less negative down, with chlorine more negative than fluorine and sulfur more negative than oxygen. Electronegativity increases across and decreases down, with fluorine at the top. Metallic character decreases across and increases down. Reducing tendency follows metallic character, oxidizing tendency generally follows non-metallic character. Oxide nature usually shifts from basic on the left through amphoteric in the middle to acidic on the right. Do not treat these as 12 unrelated arrows. Use the chain, nuclear charge rises while core shielding stays almost constant. Effective nuclear charge rises, radius falls. Ionization enthalpy and electronegativity rise, metallic character falls, oxidizing tendency rises. Down a group, a new shell and more shielding reverse the pattern. Let us enter the JEE question lab. Question 1. An element has atomic number 33. Find its period, group and block. Write the configuration: argon core 3d10, 4s2, 4p3. Highest n is 4, so period 4. The last electron enters p, so p block. There are 5 valence electrons, so group 15. The element is arsenic. Question 2. Arrange O2 minus, F minus, Ne plus and Mg2 plus in increasing ionic radius. Count electrons. Every species has 10 electrons. Compare nuclear charges. Magnesium has 12, sodium 11, fluorine 9 and oxygen 8. Higher nuclear charge means smaller radius. Therefore, Mg2 plus is less than Ne plus is less than F minus is less than O2 minus. Question 3. The successive ionization enthalpies of an element are 738, 1441, 7733 and 10540 kilojoules per mole. Identify the group. The large jump comes after the second removal. The atom has 2 valence electrons and belongs to group 2. These values correspond closely to magnesium. Question 4. Arrange sodium, magnesium, aluminium, silicon, phosphorus, sulfur and chlorine in increasing first ionization enthalpy. Start with the general across period increase, then repair the 2 exceptions. Sodium is lowest. Aluminium lies below magnesium because aluminium loses a 3p electron while magnesium loses a 3s electron. Sulfur lies below phosphorus because sulfur has a paired p electron while phosphorus is half-filled. Therefore, the order is Ne less than El less than Mg less than Si less than S less than P less than Cl. Question 5. Which is more electronegative, fluorine or chlorine, and which has more negative electron gain enthalpy? Fluorine is more electronegative because electronegativity is attraction for shared electrons in a bond. Chlorine has more negative electron gain enthalpy because it accepts a free electron into a larger 3p shell with lower repulsion. Question 6. Among K+, calcium 2+, scandium 3+, chloride minus and sulfide 2 minus, arrange the isoelectronic species in decreasing radius. Every species has 18 electrons. Compare nuclear charge. Sulfur has 16, chlorine 17, potassium 19, calcium 20 and scandium 21. Thus the radius order is S2 minus greater than Cl minus greater than K plus greater than Ca2 plus greater than Sc3 plus. For every question, see the mechanism out loud. Same electrons, compare Z.
Same period, compare Z effective. New shell, compare distance and shielding. That language makes your reasoning visible and prevents a careless memorization error. Let us finish with the 5-minute rapid revision. Start with the nucleus. Across a period, Z rises while core shielding changes little. Z effective rises, the atom contracts. Electron removal becomes harder, electronegativity rises. Metallic character falls. Down a group, a new shell is added. Distance and shielding rise, the atom expands. Electron removal becomes easier, metallic character rises. Remember the exceptions by orbital logic. Be greater than B because removing a 2p electron is easier than removing a 2s electron. N is greater than O because nitrogen is half filled and oxygen is paired electron repulsion. Chlorine has more negative electron gain enthalpy than fluorine because chlorine's 3p shell is roomier than fluorine's crowded 2p shell. For ions, cation smaller, anion larger. For isoelectronic species, higher nuclear charge, smaller radius. For chemical behavior, left is metallic and reducing, right is non-metallic and oxidizing. The periodic table is not a list, it is atomic structure made visible. Thank you for studying with JEE Prep community. Revisit the worked examples, solve the independent practice set without looking at the solutions, and always ask yourself one question. Which one has the greater effective nuclear charge? Master the why. Ace the JEE.
Welcome to the Deep Practice Workshop. We will solve 5 comparison problems by deriving the answer from electronic configuration and effective nuclear charge. Problem 1. Compare the atomic radii of sodium, magnesium, and aluminium. All 3 are in period 3. Their core is the same, the neon core, while nuclear charge rises from 11 to 12 to 13. Same principal shell, nearly unchanged core shielding, increasing effective nuclear charge. Therefore, radius decreases in the order sodium greater than magnesium greater than aluminium. Problem 2. Compare the first ionization enthalpies of sodium, magnesium, and aluminium. The general trend would be sodium less than magnesium less than aluminium, but aluminium is an exception. Sodium loses a 3s electron. Magnesium loses a 3s electron from a filled 3s subshell. Aluminium loses a 3p electron, which is higher in energy and less penetrating. Therefore, the correct order is sodium less than aluminium less than magnesium. Problem 3. Arrange nitrogen, oxygen, fluorine, and neon in increasing first ionization enthalpy. Across the period, the general trend rises. But oxygen is below nitrogen because oxygen has paired electron repulsion while nitrogen is half-filled. Therefore, the order is oxygen less than nitrogen, less than fluorine, less than neon, with carbon and boron inserted at their appropriate lower positions in the full sequence. Problem 4. Compare fluoride, chloride, bromide, and iodide in atomic radius and in electron gain enthalpy. Atomic radius increases down the group. Fluoride is smallest and iodide is largest. Electron gain enthalpy is generally less negative down the group, but chlorine is the most negative because fluorine has compact shell repulsion. So the radius order is F less than Cl less than Br less than I. For electron gain enthalpy from more negative to less negative, Cl, F, Br, I. Problem 5. A species has the configuration argon core 3d time 4s2 4p4. Identify the element and compare its radius with the element immediately to its left in the same period. The outer configuration is 4s2 4p4, so it is group 16, period 4, selenium-like chemistry. Specifically, the element is selenium if the core is argon plus 3d10 and 4s2 4p4. In the same period, the element immediately to its left has one fewer proton. The p4 element has higher effective nuclear charge, so it is smaller and more electronegative. Now a deeper isoelectronic problem. Compare oxide 2-, fluoride minus, sodium plus, magnesium 2+, and aluminium 3+. Count, each has 10 electrons. Nuclear charges are 8, 9, 11, 12, and 13. In decreasing radius, oxide 2- is largest, then fluoride minus, then sodium plus, then magnesium 2+, then aluminium 3+. If a student attempts to use charge sign alone, stop. Charge sign tells you whether the ion is larger or smaller than the parent. Isoelectronic ordering requires the nuclear charge comparison. Now use successive ionization enthalpies. An unknown has IE1 equal to 500, IE2 equal to 4500, and IE3 equal to 6000. Where is the large jump? After the first removal. That means the atom had one valence electron and belongs to group 1. If the values were 738, 1451, and 7733, the jump would occur after the second removal, identifying group D. Finally, compare the chemical behavior of sodium and chlorine. Sodium has a larger radius, lower ionization enthalpy, lower electronegativity, and strong reducing tendency because it can lose one electron.
Chlorine has a smaller radius, higher ionization enthalpy, higher electronegativity, and strong oxidizing tendency because it can gain one electron. Their oxides also differ. Sodium oxide is basic, while chlorine's highest oxide is acidic. The exam habit to develop is to say your reason in a complete sentence. Do not write only radius decreases across. Write both elements have the same principal shell, but nuclear charge increases while shielding changes little, so effective nuclear charge increases and radius decreases. Complete sentences reveal the mechanism and protect you from exceptions. Take one last pause and solve this. Which is smaller, Mg2 plus or Al3 plus, and why? Both are isoelectronic with 10 electrons. Aluminium has 13 photons, magnesium 12, so Al3 plus is smaller. The pattern is always the same. Same electrons, higher nuclear charge, smaller radius.
Before we close, let us remove the misconceptions that cause the most errors in this chapter. Misconception 1. Across a period, radius decreases because electrons are added. That is incomplete. Electrons are added, but they enter the same shell. The decisive reason is that nuclear charge increases while core shielding is nearly constant. So effective nuclear charge increases and pulls the cloud inward. Misconception 2. Ionization enthalpy always increases across a period. It generally increases but never apply the arrow without checking orbital occupancy. Beryllium is above boron in ionization enthalpy because Be loses a 2s electron, while B loses a higher energy 2p electron. Nitrogen is above oxygen because N is half-filled and O has paired electron repulsion. The period 3 analogues are magnesium above aluminium and phosphorus above sulfur. Misconception 3. Fluorine is highest in every electron attraction property. Fluorine is the most electronegative element, but chlorine has more negative electron gain enthalpy. Electronegativity is a bond property. Electron gain enthalpy is the gas phase enthalpy change for a free electron entering an atom. Fluorine's compact 2p shell creates strong repulsion for the incoming electron. Misconception 4. A cation is always smaller than every anion. The correct statement is relative to its parent atom. A cation is smaller than its parent, and anion is larger than its parent. For unrelated ions, count electrons and compare nuclear charge. In an isoelectronic series, higher nuclear charge gives smaller radius regardless of whether the species is positive or negative. Misconception 5. Electron affinity and electron gain enthalpy are identical. In many books, the terms are related, but their sign conventions may be opposite. Read the exact wording. If the question asks for more negative electron gain enthalpy, the chlorine versus fluorine comparison is Cl greater than F in magnitude of energy release. If it asks for electron affinity, using the common positive convention, the same physical ranking may appear as a larger value for chlorine. Misconception 6. Group number equals valence electron count in every block. For S block elements, the shortcut works directly. For P block elements, add 10 to the number of valence electrons. For D block elements, add the electrons in the n-1 d subshell and the ns subshell. For example, iron is argon core 3d6 4s2. 6 plus 2 gives group 8. Misconception 7. Noble gas radii break the periodic trend. The problem is usually the definition. Noble gas values are generally van der Waals radii, while neighboring elements may be listed with covalent radii. Do not compare unlike radius definitions as if they were measured in identical situations. Misconception 8. The F block is outside the periodic table. It is displayed separately for space, but lanthanoids belong to period 6 and actinoids belong to period 7. The block is determined by the differentiating F electron. Here is the exam workflow I want you to use. First, write or identify the electronic configurations. Second, classify the comparison. Same period, same group, isoelectronic, or an exception involving subshells. Third, compare nuclear charge, shell number, shielding, penetration, and pairing. Fourth, predict the trend. Fifth, check whether the property has a known exception or sign convention. When you see a statement-based question, translate every statement into a mechanism. For example, Cl has more negative electron gain enthalpy than F translates into incoming electron enters a larger 3p shell in chlorine, so repulsion is lower and energy release is greater. When you see a match the column question, write the governing principle next to each sequence before matching it. For revision, maintain one page with 5 lines. Across a period, ZF rises, radius falls, IE rises, EN rises, metallicity falls. Down a group, new shell and shielding rise, radius rises, IE falls, EN falls, metallicity falls. Exceptions, BE over B, N over O, Cl over F for electron gain enthalpy, and S over O for the same reason. Isoelectronic, higher Z means smaller radius. If you can explain each line in words, you are prepared for unfamiliar questions.
If you can only reproduce the arrows, return to effective nuclear charge and derive them again. That is the difference between memorizing the periodic table and understanding it. This completes the in-depth explanation. Use the deck for visual revision, use the masterclass notes for detailed study, and solve the questions without looking at the answers. GE Prep Community, master the why and ease the G.